Welcome to our lecture on regression discontinuity. This is another installment in a multi-part series about causal inference using observational data. And regression discontinuity is a very specific approach that can be very powerful in situations where it applies, but relies on a slightly unusual scenario. So let me describe what that scenario looks like. Here's the broad overview. We have our problem of selection bias, which is that people often get to choose their own treatment, as opposed to when we randomly assign it in an experiment, which we know would make it very easy to do causal inference. But sometimes we get lucky. Sometimes there's a legal or administrative cutoff that might either completely or partially remove this choice. The idea behind regression discontinuity is precisely to exploit these kinds of cutoffs to do causal inference. There are two flavors of RD. We're going to focus on the first one today, although we'll have a little bit to say about the second one as well. In sharp RD, the cutoff completely determines whether somebody is treated or not. So the treatment jumps from 0 right below the cutoff to 1 right above the cutoff, so that everyone below is untreated and everyone above is treated. Roughly speaking, the idea here is going to be to compare mean outcomes on either side of the cutoff. In fuzzy RD, on the other hand, this cutoff only partially determines treatment. So something jumps at the cutoff, but it's not the treatment indicator. Instead, it's the probability of treatment. So that jumps from one value to another. It's just that those values aren't 0 and 1. They're somewhere in between. With fuzzy RD, the idea is basically just going to be to use the walled estimator on either side of the cutoff. So fuzzy RD has a very close link to instrumental variables. And here is going to be my running example for today for talking about the sharp RD setting. This is a paper called Prestige Matters that appeared in the American Economic Journal Applied Economics a few years back. This is about the effect of attending more elite universities on wage and also how much you learn. So this has a lot to tell us about things like signaling and human capital formation in the labor market. All right, so the research question in this paper is, what is the causal effect of attending an elite college on later life outcomes? Here is the background. The most prestigious colleges in India are in fact public rather than private, and admissions to these public colleges is determined by a threshold rule. You take a senior secondary school exam, and if your score is above the threshold, you're admitted. Otherwise, you're not. So the causal identification here will be comparing students with scores just below the threshold to those just above. The idea, and this is what we're going to lean on very heavily, is that being just slightly below the cutoff versus just slightly above the cutoff really doesn't make a difference in terms of your characteristics. So we're going to be assuming that these people who are just below and just above are practically identical. So if that's the case, then it's as if going to an elite college was randomly assigned for students whose scores are near to that cutoff. Again, the idea is that if people on one side of the cutoff and just on the other side of the cutoff are effectively identical, then it's as though we really are running a randomized controlled trial for those people right near the cutoff. So we know that whether you go to a public college or not jumps at the cutoff. So we're going to try to see if later life outcomes also jump at this admissions cutoff. In some sense, sharp RD is extremely simple and extremely intuitive, and everything that comes next is really just details of how to implement it. So here's a picture. I'm going to use the following notation. 1 of A is the indicator of the event A. This equals 1 if A occurs and 0 otherwise. So the assumption that we'll make in sharp sharp RD, is the following. This is the sharp RD design. We have a binary treatment, D, and that is equal to the indicator of X being greater than or equal to some cutoff C. X is an observed scalar variable that we call the running variable, and C is a known threshold. So we can observe X, and we know C. Everybody who has the value of X at or above the cutoff is treated, so they have D as 1, and no one who has a value of X below the cutoff is treated. They all have D as 0. At the right-hand side of the slide, I have a diagram that illustrates this with the indicator function, using red for untreated and blue for treated. Sounds familiar, right? It's a little bit like selection on observables. So in particular, the selection on observables assumption actually holds. So let's check why this is the case. So D, in this context, is just equal to the indicator that X is greater than or equal to C. That's a measurable function of X. In other words, it's a function whose value we know if we know X. Okay, so what does that imply? Well, the mean of y1 given D and X is the same thing as the mean of y1 given that indicator function and X. Okay, but if you take a look at what's in the conditioning set, now we're conditioning on X and also the indicator that X is above or equal to some known cutoff, C. So there's no, if you already know X, there's no additional information contained in that indicator function. So we can just drop it from the conditioning set, and we end up with just the expectation of y1 given X. The same exact thing goes for the y0 equation. So what we're showing here is that, in fact, D, the treatment, is mean independent of the potential outcomes conditional on X. So we have selection on observables. And you might be asking yourself, why do we need a lecture on regression discontinuity? We've already covered selection on observables. Can't we just use that? Well, the problem here is that there were two assumptions needed to implement a selection on observables strategy, like regression discontinuity, I should say, like regression adjustment or propensity score reweighting. So the problem here is that the second condition actually fails, and that condition was overlap. So remember that the overlap condition required there to be some treated and some untreated people for every value of the covariance X. But here, the running variable completely determines treatment. So at a given value of X, either everybody is treated or nobody is treated. And that means we can't compare people with the same X but different Ds as we did in this propensity score weighting and regression adjustment case. So we need a new approach. All right, here's the key intuition. As I mentioned before, students whose test scores fall in a sufficiently small neighborhood of the admissions cutoff must, in some sense, be effectively identical. That's the idea. We're going to lean very heavily on this and use it to learn a causal effect. Identical how, though? Well, what we need is for the treatment to be the only thing that jumps at the cutoff. So what do I mean there? Well, what are y0 and y1? These are potential wages. So they're potential wages in the state of the world where you don't go to an elite institution and where you do. And probably those are related to your secondary school test scores. So probably y0 depends on X, and so does y1. That's fine. So D jumps at the cutoff. That means that at the cutoff, y is going to jump from a value of y0, just to the left of the cutoff, to a value of y1, just to the right. So what we need to rule out here is we need to rule out a jump in the potential outcomes themselves. So we need to assume that as a function of X, y0 does not jump at the cutoff, and y1 does not jump at the cutoff. So the only thing that jumps is D, and we basically switch from one curve for y0 to a different one for y1, and I'm going to show you a picture of that in one moment. Formally, the assumption that we need here is that the conditional mean functions of y0 given X and y1 given X are both continuous at the point C, so continuous at the cutoff. How could that assumption fail? Well, a key way that that could fail in the example we're looking at today is if students could precisely manipulate their secondary test scores. For example, suppose that students could predict whether they're likely to score just below the cutoff. Well, if they could predict this accurately, then that might cause very diligent students in the situation to put in extra effort. If that's the case, then that could cause a jump in diligence at the cutoff. And if diligence is related to later life wage, that would create a problem. So is this an issue? Well, it depends on whether we can generate another discontinuity besides D. In the particular example we're looking at, this seems unlikely. The reason is that students don't actually know what the cutoff is going to be, because it changes from year to year and subject to subject. So if they don't know the cutoff, then it's going to be very tricky for them to precisely manipulate whether they fall above or below it. So in some sense, the plausibility of this assumption has a lot to do with whether people have any ability to respond to knowledge of where they're going to fall relative to that cutoff. When it's plausible that they don't, then the continuity of conditional means is going to be quite a plausible assumption. As promised, here is the picture. Let me take a bit of time explaining this. So we have two curves in this picture. First of all, we have a curve which is the expected value of y1 given x. I show that in a dashed blue line, which then continues to a solid black line to the right. Second of all, I show the conditional mean function of y0 given x. I show that with a dashed red line to the right, which continues to a solid black line to the left. So why am I distinguishing these different colors? Well, suppose that you are someone who has an x value below the cutoff. Then for you, your observed value of y is equal to y0. So the first chunk of the function expectation of y given x, this black line to the left of the diagram, coincides with a portion of the expected value of y0 given x. In other words, to the left of the cutoff c, the conditional mean of the observed outcome given x is the same thing as the conditional mean of the potential outcome y0 given x. But as soon as we get to the right of the cutoff, we switch. So as soon as you hit c, we go from y being equal to y0 to y being equal to y1. So from then on, the conditional mean function of y given x is equal to the conditional mean function of y1 given x. In other words, the average wage as a function of test score is equal to the average treated potential outcome given test score. So the black curve is what we can actually observe in the data. It coincides with a portion of each of the dashed curves, depending on whether we're to the right or to the left. So the dashed blue line is the portion of the conditional mean function of y1 given x that we can never observe, because we're never going to observe anybody with a y1 outcome when they have a test score below c. Similarly, the dashed red curve is the portion of the conditional mean function of y0 given x that we can never observe, because anybody above the threshold c is treated, so we can't observe any y0 outcomes for people with x above the cutoff. Right at the cutoff c, which is precisely where the jump happens, I've drawn a gap. That gap is labeled tau s. So here s stands for sharp, and this tau s is exactly equal to the difference of the expectation of y1 given x when x is c, and the expected value of y0 given x when x is c. So this tau s is the causal effect of attending an elite institution on your later life outcome y for the sort of person whose test score is exactly equal to the cutoff. In other words, tau s is the conditional average treatment effect when x is equal to c. How could we ever learn this thing? Well, the way we could learn it is we could look for a jump in the observed conditional mean function, y given x, because the jump in that observed conditional mean function precisely coincides with the difference in the y1 and y0 potential outcome functions at the point c. And notice that this is the only point on the diagram where we have any hope of learning that causal effect. The reason is that's the only point where we actually observe some test scores. I should say where we actually observe some people in each of the treatment states. So just below C, we're observing these untreated people. Just above C, we're observing these treated people. And we're basically going to fudge the fact that those are slightly different test scores and compare right below and right above that threshold to see if there's a jump in expectation of y given x. That's really all there is to sharp RD. And, again, I have actually written out a formal proof of this. It's not that exciting. I would encourage you to take a peek at it. You can, if you like, you can also take a look at my lecture notes on treatment-effects.com. But really, there's nothing else going on here besides that picture. We're just going to take limits, we're going to use the continuity, and we're going to use the definition of the treatment, D, as being determined entirely by whether you're below the threshold or above. So I don't think there's a tremendous amount to be gained from my talking you through this slide, but by all means, if you like, pause, read it, think carefully, and again, you can take a look at the associated chapter in my treatment effects slides available from treatment-effects.com, which will walk you through this in great detail. So what does this actually tell us to do? Well, it tells us that we would like to take the limit from the right, so the limit as x decreases towards the cutoff c, of the conditional mean function of y given x. We would like to take the limit from the left, in other words, the limit as x increases towards c of the same conditional mean function, and the difference of those two is going to be exactly equal to the conditional average treatment effect when x is c. That's exactly the same intuition from the picture, and the reason why it works is because we have assumed that there is no jump in each of the separate conditional mean functions at that point. So let me just for a moment go back to show you this. If you trace out the blue dashed curve to the point where it meets the black curve at the top of this diagram, you'll see there is no jump in the expected value of y1 given x. It's increasing. So the way that I've drawn things here, people with higher test scores have better later life outcomes, but that is a smooth curve. Similarly, the lower curve, which is the expected value of y0 given x, the dashed red curve, which connects to the solid black curve, there's no discontinuity in that curve. It's increasing, so people with higher test scores are having better later life outcomes, but there's no jump. The thing that jumps at the cutoff is that we switch from observing the y0 function to the y1 function. If there were some kind of a jump in those separate functions, that would invalidate the approach. So again, everything that there is to know is in the picture, and in some sense, the proof is really just bookkeeping that turns that picture into more precise mathematics. So let's take a look at the empirical example. Here I am showing two figures from the paper that I mentioned before. Let's focus on the left-hand picture. So this shows mean salary later in life for the students in the paper, the students whose observations are used in this paper. And the cutoff here has been normalized to 0. So the way that this works is there's a different cutoff in every year and in every subject, and the scores have all been shifted around so that all those combinations of year and subject are redefined to make 0 the threshold for getting in versus not. That just makes things much simpler. So what the author has done is estimate that conditional mean function of expectation of salary given the exam score below the cutoff of 0 and above, and has done this with basically with a linear regression. So we have one line below the cutoff, which is fairly flat, and we have another line above the cutoff, which is a little bit steeper and is declining. Now, one thing I want to comment on is the little green points that you see in this diagram. Those are not, in fact, the raw data. For reasons that I personally find a bit strange, in the applied literature, people tend to bin the observations and compute means inside of the bins rather than showing the raw data. I really don't like that. Bruce Hansen also does not like that, so at least I know I'm not alone, but it's what's widely done in practice. So just to be clear, these green points are not the data. They're actually a kind of model of their own. So it's best to just focus on those lines for the moment and not worry too much perhaps about those green points, but we can also talk about them a bit. The key thing we're looking for is whether there's a jump at the cutoff. and the cutoff again has been normalized to 0? The answer is yes. There's a very big jump. So the people who are just below the cutoff appear to have a substantially lower mean salary later in life than those who are just above. I am struggling at the moment to remember how the mean salary has been normalized, but what I do remember is that I checked that this difference is actually quite large relative to the salaries in question. Now, going back to the idea of those green dots, you could take a peek at the green dot just below the cutoff and the one just above. So those are actually just the mean salaries for the people in a bin that's right below and right above the cutoff. So if you don't like the lines and you want to think instead about just like a simple difference of means, that's what those 2 green points are showing. So there's a big jump right at that point. And if we assume that students can't precisely manipulate their test scores, then what this shows is that for the sort of person who's right near that cutoff, there's actually a big causal effect of attending the elite public institution. It causes much higher later life wages, which is very interesting because if you turn your attention to the right-hand side of the slide, you can see a comparison of exit test scores. So something that I did not mention about the institutional environment in which this study takes place is that these public and private colleges in India, they actually cluster inside of the same universities. So they cluster inside of the same degree-granting institutions. So in the same university, you can have a public college, you can have a private college, and what's interesting is that the students who are studying the same subject will all take the same exit exam when they finish the degree. So we have seen that the graduates of the elite institutions earn more, which is to say that there is a large causal effect of attending the elite institution on your wage, at least for people near the cutoff. But do they learn more? Well, again, we want to look at this line just below the cutoff of 0 and just above. And there's really nothing going on here. So interestingly, it seems that, at least for the people who are near this cutoff, there's really no causal effect on what they learn, at least as measured by exit test scores. But they earn a lot more, which I suppose would cause us perhaps to doubt, to some extent, the human capital model, and perhaps give a little bit more attention to the signaling model. Now, what have we actually learned here? That's actually a very important question. And the answer is, well, we've only used data from close to the cutoff. So we fitted one regression model to the left, one regression model to the right, and we could implement this using, and I'll show you this in a moment, a treatment dummy interacted with X. Okay, and so this is a perfectly valid idea, but it raises a whole bunch of different questions for implementation. First, how close is close? So ideally, we would only want to use observations that are really close to the cutoff. This would mean that we have low bias, because as we move away from the cutoff, it becomes less and less reasonable to assume that these students are similar. Students with very different test scores are likely going to have very different wages later in life. So it's only close to the cutoff that effect, the effect of the difference in test scores on later life wages, is small enough that we could ignore it. The key, again, is continuity. So continuity says a small change in the test score does not cause a large jump in the y0 or the y1 function. So the only thing that's jumping is the treatment. The problem, of course, if we look really close to the threshold, is that there are very few observations. So this causes a high variance estimator. There is also something a little bit worrying about nonlinearity here. So we might like to allow the conditional mean function to be nonlinear to avoid confusing a genuine jump with just a sharp bend in a function. I'll show you an example of that in a moment. But you have to be very careful. So it's quite dangerous to just fit polynomial regressions on either side of the threshold, especially if they're higher order polynomials. There's a nice article by Imbens and Gelman that I definitely suggest that you check out. You can click on this link from the slides. There are also many implementation details if you want to take a non-parametric approach to this estimation, which is something you can do. I've linked to a good article here for you. And there's also a classic review article on RD. It's by this point, it's getting quite dated, but it's still really valuable. And if you're going to be using RD in your own work, I would definitely suggest starting there. Okay, so now let me show you how we can implement this. I'm going to suppose we want to run linear regressions on either side of this cutoff. So suppose that for x below c, we want to run this linear regression of y on x with coefficients alpha 0 and alpha 1. And for x greater than or equal to c, we want to run the linear regression of y on x with coefficients beta 0 and beta 1. So what do we get out? Well, from this formulation, the conditional average treatment effect when x is c will be equal to beta 0 minus alpha 0 plus beta 1 minus alpha 1 times c. We get that by simply subtracting those two linear regressions from each other at the cutoff. Because again, remember, that is precisely the location of the jump, and under this continuity assumption, that jump will precisely be the average treatment effect for the sort of person who has a test score right at the cutoff. Now, it's a little bit inconvenient to actually run that regression separately for each side. So instead, what we could do is we could implement this using a single regression with an interaction. All right, so here's how we could do that. We could regress y on d, the treatment dummy, x, and the interaction of d with x. If we do that, well, then we'll get these coefficients gamma naught, gamma 1, gamma 2, and gamma 3. And then there's a relationship between those gammas and then the alphas and betas at the top of the slide, so that to find the causal effect of interest, we would need to take gamma 1 plus gamma 3 times c. Now, but this is also not terribly efficient. It's sort of a pain because, when we learn the gamma 1 and the gamma 3, then we've got to process them and multiply by c to get the overall causal effect. And then we have to try to figure out what the standard error is, and that's going to be tricky because gamma 1 and gamma 3 hat will be correlated. And now if this is beginning to look a little bit familiar, you may remember that we ran into something similar when we looked at regression adjustment in our lecture on selection on observables. So in fact, a very similar solution works here, such that we can run a single regression that very conveniently gives us the causal effect that we want as one of the coefficients in that regression, and also gives us the associated standard error. So here's the way to do it. Simply redefine the running variable. So take x, take the known cutoff c, subtract, and call the result x tilde. Now, if you run a regression of y on d, x tilde, and d times x tilde, then the coefficient on d will be your causal effect of interest. And if you want to see why this works, you can go through the algebra here. You can also go back and take a look at the example from our selection on observables lecture. It's very similar logic. Now let's give it a try. So I'm going to generate some data in a moment. So I first need to set up the parameters. I'll set up the alpha and beta parameters of those separate regressions. And then I'll work out what the implied parameters of that joint regression would be. And then I will simulate from that joint regression here. By now, this is starting to look pretty familiar. I think I'm going to set a cutoff of 0.5. So d will be 1 to the right of the cutoff, and it will be 0 otherwise. I'll generate some standard normal noise in y. And just to make life simple, I'm actually going to generate my x to be uniform. And then I will simulate from a single regression model here that combines both halves, the two lines on either side of the threshold. And now I will just show you that my proposed approach actually works. So let's take a look. I will take x, I will subtract the cutoff, then I'll run a regression of y on d, x tilde, and their interaction, which I can do very succinctly using this asterisk notation. Remember that that means something different inside of an R formula than it does in other environments. And I will then tidy the result. So my causal effect estimate here is the coefficient on d, which is about 0.27, and you see that I also get my standard error of around 0.02. So it's very convenient. And we can also take a look at a picture. Here, I am showing you the raw data. I'm not doing that funny thing where I average the data into little bins because I think it creates a misleading interpretation, kind of a misleading impression of the variation in y. So again, this is a simulated data example. It's not a real data example. But I am showing you here how you can use ggplot to make a plot like this, where we actually have different regression lines on each side of the cutoff. And it's very convenient in ggplot because we can basically just supply an additional argument to the aesthetic mapping. You see here I'm supplying color equals factor D. So I'm converting D to a factor, which is R's name for a categorical variable. And I'm using color, which, remember, it's another one of the sort of dimensions that we can play with in an aesthetic mapping. I'm using color to map that particular piece of information. So when I pass that through to my geom point and my geom smooth, notice what's happened. ggplot has realized that it needs to run separate regressions depending on that factor. And it's displaying them nicely with different colors, so everything looks awfully nice, and it's pretty easy to generate. I mentioned a few slides back that there is a risk of confusing a sharp bend in a function with a jump. Unfortunately, it's basically impossible to tell whether a function has a genuine discontinuity. But what you can do is you can allow for a little bit more flexibility so that at least if there's a sharp bend, we can pick that up without confusing it with a genuine discontinuity, because we might expect bends to be a little bit sharp, maybe not too sharp. So for example, we could maybe allow for some curvature, and we could see whether we still find a jump when we allow for that curvature. Maybe it sounds a little bit like black magic, and to some extent it has to be. But this can help us to avoid some really obvious mistakes. So what I'm going to do here is I'm going to generate a non-linear relationship between y and x, and it's one in which there is in fact no discontinuity. So if you take a look at the way I'm generating y on this slide, in terms of x, I'm actually using the normal CDF, which is sort of an S-shaped curve, so that initially there's no effect of x on y. Then there starts to be a very steep relationship, and then it flattens off. And around that S-shaped curve, I have added normal random noise. So I should get a sort of fuzzy-looking S shape here. As before, my treatment dummy is going to be 0 to the left of the cutoff and 1 to the right. Let me now run exactly the same kind of regression as I did before. Here, I'm just specifying that regression formula in a slightly different way. Previously, I used the asterisk. And I'm just showing you another way to do it, of course, is to use a colon, in which case you've got to specify d plus x tilde colon d. If this looks unfamiliar, you can go back and take a look at our lecture on linear regression, and you can also read my blog post on formula syntax in R. All right, so, well, what was the causal effect of d in this case? Let's go back to the simulation. There isn't one. D has no causal effect on y, but look at the coefficient on D in the regression. It's about 0.5, and the standard error is pretty small. So if we ran this linear regression on each side of the cutoff, we would confuse what is in fact a bend in the function with a jump. You can see that in the picture here. The linear regression model is getting fooled by the curvature in the region around the cutoff. As a consequence, it's trying to fit the points far to the left of the cutoff with a line and doing a bad job with the points right near the cutoff. Similar ideas going on to the right. But if we actually look at the points that are right near the cutoff, there's no jump there that we can see. So there are kind of two lessons to be seen here. One is if we fit this kind of global trend on each side, we're going to try to do a good job on average across all the points, but the place that we really care about is near the jump. So back to this bias variance trade-off idea, we'd really like to restrict our attention to places near that jump. Of course, the cost of doing so is there are fewer observations, there's going to be more estimation uncertainty. But similarly, using a simple approximation like a line kind of forces us to miss curvature that could actually lead to us confusing a bend with a jump. Now, in this particular scenario, it's not too hard to fix things, because even though that S-shaped curve is actually the normal CDF, we can do a pretty good job approximating it by just putting a quadratic on either side of the cutoff. So that's what I'm going to do here. Again, using some R formula syntax that I hope will be relatively familiar to you. So I'm now going to include in my regression x tilde and also x tilde squared. I have to wrap that inside of the I function so that it's treated as is within the formula. And then I'm going to have each of those in levels, and also each of those interacted with d. That's what the asterisk does for me. Now, the same logic as before is going to go through. It's going to be the coefficient on d that gives me the causal effect. And now we see that that causal effect is close to 0. It's still not perfect, but it's much better than it was before. And 0.09 with a standard error of 0.6 is not going to confuse us anywhere near as much as what we had previously. So that's everything that I'd like to say about sharp RD. There's a lot more that can be said in terms of the precise details of implementation, but we've really covered the key ideas of causal identification, and we've talked a little bit about some of the basic issues that arise in estimation. Now I'd like to briefly turn our attention to fuzzy RD. And to do that, I'm going to briefly talk about a second applied example. This one is by Jacob and Lefgren, and it's in a 2004 journal in the Review of Economics and Statistics called Remedial Education and Student Achievement, a Regression Discontinuity Analysis. The research question in this paper is about the causal effect of remedial education. That's defined to mean sending kids to summer school, in other words, making them keep going to school over the summer rather than taking the time off, and also making kids repeat a grade, so holding them back a year in school. The background here is that the Chicago public schools used to practice what is called social promotion. Students would advance to the next school grade regardless of their academic performance. Between 1996 and 1997, however, there was a policy change that introduced achievement thresholds in the 3rd grade, the 6th grade, and the 8th grades. This put an end to social promotion. You had to pass math and reading tests at these key thresholds in order to advance. So here's how it worked. In June, you took a test. If you passed that test, you would automatically advance. If you failed, you would attend summer school and retest in August. If you then went on to fail in August, you would repeat a grade in school. So why is this an RD design? Well, it's because administrative thresholds determine treatment, namely summer school / repeating a grade. But why isn't it a sharp RD? Well, the point is that the administrative threshold actually in practice only imperfectly determined treatment. So it turned out that 3% of the students who failed in June were nonetheless exempted from summer school. And similarly, 14% of the students who failed the August retest were exempted from repeating a grade. It was also the case that some students were required to repeat a grade despite passing in June. So what this means is that the probability of treatment jumped at the cutoff, but it did not jump from 0 to 1. So we could think about this by saying that the limit from the left of the probability that d equals 1 given x was not equal to the limit from the right, but these two were not equal to 0 and 1 respectively. They were equal to something else, because the rule that the administrative threshold was supposed to put in place was only partially obeyed. So what do? Well, it turns out we just do IV right around the threshold. So the idea is very, very, very similar to a plain vanilla IV. We're going to form the walled estimand. We're just going to put limits. So the numerator of this walled estimand, which is like the intent to treat, is precisely the same thing that we used in a sharp RD. So we're looking at the limit from the left, just below the threshold of the conditional mean function of y given x, and we subtract from that the limit from the right of the conditional mean function of y given x. So we're looking for the jump in y right at the threshold, the jump in the average value of y right at the threshold. But what we now do is we divide that by another jump. We divide that by the jump in d given x. So if you think about what this would be in the sharp RD design, the denominator would be 1 minus 0. So in the fuzzy RD design, we're simply saying, listen, there's a jump in treatment that occurs at the threshold, but it doesn't go from 0 to 1. Let's find out where it starts and where it ends, and let's divide by that difference. So that's all that happens here, and it's pretty much exactly like a walled estimand. So, the idea here is very similar to IV. If you've recently watched that lecture on IV, this gives you the rough idea. And in terms of implementation, you can basically do this as an IV that's also near the threshold. So if you do take a look at the Jacob and Lefgren paper, you can see some more details. Just one thing to be aware of is that in their paper, they've sort of reversed the definition of the running variable. So you just have to flip it around to see how this relates to the discussion here, but the basic idea is the same. So just to summarize, regression discontinuity can be a very useful and very powerful tool. It exploits an administrative cutoff that partially takes away choice, such that people can either not choose their treatment at all, or they have limited choice. When this assumption holds, we have an excellent opportunity to learn an interesting causal effect. The catch is that we're only learning that causal effect right near the threshold. So again, we find ourselves in a situation where the causal effect that we can learn might not be the causal effect that we're actually interested in. There is some work about trying to generalize the results that you get from a regression discontinuity design to extrapolate beyond the threshold. There are some assumptions that can allow us to do this, but they are stronger assumptions. And fundamentally, there's no free lunch. As I said before, you can't do causal inference without assumptions. And even if you do make assumptions, you might not always get what you want. Regression discontinuity, while very powerful, is no exception to this general rule.